Introduction to diffraction. Everyone is used to the idea that sound bends around corners. Sound didn't behave this way. You couldn't hear this instructor's words when his back was turned toward you. The bending of waves around obstacles is the fundamental behavior of all waves. What may surprise you is that light can bend around corners as well. To show you what I mean, I'm going to use a diffraction applet by inkser.netfirms.com. So what you're seeing on this applet is that these are the incoming waves, and there's a single opening. But more importantly, it's this obstacle here and here. But one of the things that you see here is that if I was to think of light as being a ray, then the light coming smack through the middle is the only light that you could see. But there's an issue here. If you were to think of light as a ray, then to the right behind this barrier, this is the geometric shadow. That means no light should be in here. But you can see here that there are regions of constructive and regions of destructive interference. Looking at an image of the app, I have incoming waves that have some wavelength. There's a slit opening, which is defined by little a, which is how big that opening is. There's a geometric shadow area. That is, behind the barrier, if I was to think of light as a ray, there should be no light here. But there is. The geometric shadow area, you observe constructive and destructive interference. So if you look in here, these waves are in sync, as well as here, as well as there. But then I get that blurred region, which indicates that you have destructive interference. Last thing that I'll comment on is that if you look at the brightness of the central maxima, the secondaries are much dimmer than the central max. That is quite contrary to interference. Interference has all maximas with the same brightness. Not true for this diffraction pattern. There's a subtle difference between interference and diffraction. Interference effects due to combining many light waves is referred to as diffraction. There is no fundamental distinction between interference and diffraction. One cannot separate out the two. They are both always present. Diffraction is sometimes described as the bending of light around an obstacle. This is not related to the bending due to refraction. When part of the wave is cut off by some obstacle, we observe diffraction effects that result from interference of the remaining parts of the wavefront. This will be a conceptual hurdle for you, and I have not explained any parts of this yet, but I will very soon. Diffraction from a single slit. To try to get a handle on diffraction, I will summarize both interference and diffraction simultaneously, because they have many similarities. Two-slit interference. There are 4 key details. The distinguishing parameter of interference is the slit separation little d. So if you see little d, you know you're talking about interference. The parameter that describes how much interference occurs is the interference parameter, which is equal to d over lambda. Carlos's language, you won't find this on the web. In other words, if d over lambda, the interference parameter, is small, there are few interference fringes. Therefore, I say that that's small interference. If it's large, then I have numerous interference fringes, so therefore I have lots of interference or large interference. The path difference equation determines the angular location of bright and dark fringes. In other words, delta r equal to d sine theta is then going to be m lambda for constructive, and m plus 1/2 times lambda will be destructive. Location of the fringe on the screen is given by y of m, which is d tan theta of m. Again, this tan theta of m implies that we're using a small angle approximation. Spacings between consecutive bright and dark fringes are equal. That is, delta y bright is equal to delta y dark. 3. The number of bright or dark fringes are determined by calculating the sequence for sine of theta m equal to mc lambda over d, where then mc is 0, 1, 2, etc., etc., until sine of theta m is greater than 1. That was for bright fringes. For dark fringes, I can do the exact same type of sequence, where I replace MD with 0, 1, 2, etc. until sine of theta m is greater than 1. Aside, the meaning of the interference parameter is best understood here. Starting with sine of theta m equal to MC lambda d, I'm going to solve for MC. We find here that MC is equal to sine of theta times the interference parameter. If I look at the maximum value of MC, we can see that it's equal to the interference parameter. So if I have a high interference parameter value, then it means I have more MC values, therefore the waves interfere more. If I have a small d over lambda, then I have less interference patterns. 4. The intensity function is the relative intensity is equal to cosine squared beta, where beta is a phase factor which is equal to pi d lambda sine of theta m. Here's a plot of the relative intensity with respect to beta. One of the key things about interference is that all of the interference maximas are at the same height. They have the same maximum intensity. So when I'm looking at MC, the central fringe is 0, and then of course we go off to the right with 1 and 2, etc., and then the negative numbers to the left. The beta factor tells us essentially when this relative intensity is a maximum. And so at 0 I get a maximum because cosine at 0 is 1. So then I get pi, 2 pi, minus pi, and minus 2 pi. Single-slit diffraction. The setup for single-slit diffraction is exactly the same. The setup for single-slit diffraction is exactly the same as interference, except that now we have a single slit. I have light of a certain wavelength impinging on a surface that has a small opening. That small opening is called the slit opening, A. I have a distance to my screen, which is capital D. The most distinguishing parameter of diffraction is the slit opening A, or the size of a single obstacle, which is labeled A. The parameter that describes how much diffraction occurs is the diffraction parameter, which is equal to A over lambda. As with the interference parameter, this phrase diffraction parameter is not a common language. This is Carlos's language so that you and I can communicate. What the diffraction parameter implies here is that if A over lambda is large, then there's lots of diffraction. On the other hand, if A over lambda is small, then you get very little diffraction. 2. The path difference equation only determines when dark fringes, which I now call minimas to not confuse the language with interference, are located angularly. The path difference equation is A sine theta equal to ND lambda, where MD is the minimum number and it's equal to 1, 2, 3, etc. 2 key points to note. This equation, A sine equals to N lambda, is an exact equation. Note that the minimum number, ND, there's no zero value. There is an approximation for the angular locations of the bright fringes, but I won't call them bright fringes, I'll call them maximas. The path difference A sine theta sub n is approximately equal to NC plus 1/2 times lambda, where NC is the maximum number, which once again there's no zero value. It starts at 1, 2, 3, etc. This equation is not exact until NC gets really large. The screen location of minimas and maximas is given by the expression y of n equal to d tan theta, just like we saw with interference. But it is common for the small angle approximation to not be valid for diffraction. So one has to have caution when dealing with these. The spacings between minimas on the screen are exactly the same, but it's not true for the maximas. So if I look at the spacing between the minimas, That's always a constant. Another thing that's really unusual is that the width of the central max is exactly twice that of the minimas. And the locations of the minimas, their spacings are not the same. It's not a constant. 3. The number of minimas, ND, or maximas, NC, are determined by calculating the sequence, that is n equal to 1, 2, 3, for the path difference equation. From the path difference equation, I get sine of theta sub n is equal to nd lambda divided by a. So now if I put in my sequence, I get 1 times lambda divided by a, 2 lambda divided by a, 3 lambda divided by a, and I keep going through this sequence until sine of theta n is greater than 1, which then stops it. This guy right here was for the minimas, but for the maximas, an approximate value would be that it's nc plus 1/2 times lambda divided by a. Again, if I follow the sequence, and I can go until sine of theta n is greater than 1. As an aside, similar to the interference parameter, the diffraction parameter is best understood from the path difference equation. Starting with sine of theta equal to nd lambda divided by a, if I solve for nd, I get that it's equal to sine of n times a over lambda, but the sine value is maximal at 1. So then the maximum value of nd then is equal to this diffraction parameter. So in other words, if I have a high diffraction parameter, I have more minimas. If I have a smaller diffraction parameter, I have less minimas, which tells us about how much diffraction is actually going on. The relative intensity function for diffraction is I of a single slit is a function of alpha, and that's equal to the sine of alpha divided by alpha squared, where alpha is pi a divided by lambda times sine of theta, and this is a phase factor, very similar to beta. So if you plot the intensity function, what you'll find here, you'll get a broad maximum, and then you have secondary maximas. So if I look at this broad central max, it turns out that it's twice the distance of the spacings between the minimas. The secondary maximas are equally spaced between two minimas, but what you're going to find here is that the location of the max here and here and here are not exactly in the middle between the minimas. More on this later. Let's do a summary of all of this information that was just covered. I have the headings of the type of interference, constructive and destructive. I purposely reversed it for diffraction. I have what's called the fringe and the minima number, the path difference, the phase, and the relative intensity. So for interference, here's what I get. If I have constructive, I have MC equal to 0, 1, 2, 3, etc. And then the path difference is d sine theta of m is equal to MC lambda. Whereas destructive, I got MD equal to 0, 1, 2, etc. And then I have the path difference here is going to be MD plus 1/2 lambda. The phase factor is beta, and the relative intensity is cosine squared beta. But when you look at diffraction, note that there is no n value equal to 0. So when I look at destructive interference, it occurs with the relationship that looks exactly, except for the A replaced with the D, with maximas for interference or bright fringes and minimas for diffraction. And if I look at the relationship between the location for angular location for dark fringes, it looks almost identical to the location of maximas for diffraction. But if I look at the phase factor, you can see that they're identical except for the D and the A. The big difference, of course, is the relative intensity, where this is sine of alpha over alpha squared. But they look very, very similar. And remember what I said in the past. There is you can't separate interference and diffraction. They always happen simultaneously.